Now that we have looked at basically how do you deal with a finite difference time domain methods in space and time. Space and time updates is what we have seen. Now we have to actually get into the details of the numerical analysis of FDTD. So this is relatively a new thing which we did not study in the case of integral equation methods or finite element methods, okay. And that is coming because now we are dealing with time explicitly. So, for example, a question that can come over here is, does the solution have stability? Does it converge or does it explode? In the case of in the previous methods, we took e to the j omega t, so it always was having a time harmonic behavior. Here it is not guaranteed. So, we want to study under which conditions, are there any conditions. So, what are the main parameters that we have seen so far in the FDTD? The discretization, delta x, delta y, delta z and delta t. And so far we have not given any constraints or any design principle that you should choose it to be this much or that much. So, how do we know what values of delta x, delta t we should choose in order for us to get a solution which has physical meaning, right? I can run the procedure for any delta x, delta y, delta t, does not mean it is the correct answer. So, this is the part where we study the numerical analysis of when will I get a meaningful solution, okay. So, the stability criteria that we will look at is something very simple. What we will do is we will take a trivial example where I know the true solution, okay, and I will compare that with the computed solution from FDTD, and we would want both of those to be the same or at least control the error. So, let us see under what conditions does that happen. So, what do you think is the simplest simplest solution to Maxwell's equations? We will pick that and then we will solve that. So, you want what about Maxwell's equations in free space? No current, no sources, nothing, right? And we know the solution is plane wave, right? So, this plane wave comes to our rescue many times, okay. So, let us start with the plane wave idea. The plane wave we know again in one dimension, we will just take it very simple, satisfies the wave equation. And we already know that this has analytical solutions of which form? Plane wave, right? I mean, so it is what? E to the j kx plus minus omega t, right? We know that these are the solutions to this equation. So, it is very good, we have a reference solution. Now, when we begin to discretize these equations, what would you do? How would we discretize these equations? So, first of all, let us see what order of derivative is there, second order derivative, right. So, when I write, I will use Taylor's theorem because that is what we had used. So, f of z naught plus delta z by 2, okay. First term f of z naught plus delta z by 2 f prime z naught. I will also include a second order derivative. Okay. So, now I have got Taylor's approximation up to, I have written it up to the second order. And I want an approximation for what? The second order derivative, right. So, similarly, I can write down for f of z naught minus delta z by 2, right. Same term minus same term plus, that is the format. So, now if I want to approximate the second order derivative, what do I do to these two equations? Add, subtract, multiply, divide, what do I do? Add these two equations. If I add these two equations, I want an approximation, see the wave equation has second order derivatives. So, I want an approximation for second order derivatives. So, if I add these two equations, so this says that I can just bring it already on one side, f prime of over here. So, what all terms will I have? When I add it over here, So, I will have f of z naught plus delta z by 2, then minus 2 f of z naught plus f of z naught minus delta z by 2. Okay. What goes in the denominator? So, there is going to be an overall 1 by 2, right. So, this factor of half and half will become 1, right, and delta z by 2 whole square. Is that right, or are we missing any term? So, in general it's I mean, yeah, okay, you can just leave it at this. This is the plus higher order terms, okay, which we need not worry about. So, this was, let us call this equation 1 and this is now equation 2. So, if I put now this 2 into 1, I can apply this to space, I can apply this to time, right. So, let us write down the first term, right. So, it's this is what I want to do. Now, I am looking at electric fields on the grid, okay. So, space derivatives. So, where all do I know electric fields? In space, how far apart are electric fields? Delta x, right. So, so what should I write over here? First, in our shorthand notations, all of these will happen at the same time, but at different locations in space. So, En, okay, what should I write? I plus 1, I plus half, I minus half, what should the first term be? There is no j, let us make it 1d. So, which the grid points are just numbered by integers 1, 2, 3, 4, I, right. So, z naught plus delta z by 2. So, this delta z by 2 is what? It is the next grid point, I plus 1, okay. If I take z naught to be I, so it is 1 into the right. So, it is I plus 1, next term is minus, I am choosing I to denote z naught. So, in what I wrote over here, f is evaluated at 3 points, z naught plus delta z by 2, z naught and z naught minus delta z by 2. So, what is the spacing between two adjacent points? Delta z by 2, that is my delta x, because that is where I am storing my electric field, right. So, this term will become 2 times right. Next final term is easy, it is what? E, time index is n, space index is I minus 1, because it's z naught minus delta z by 2, right, the previous one. So, think of the time, think of space like this, x, this is I plus 1, this is I minus 1, okay. So, graphically what is the second derivative, right, it's the combination of the function evaluation at these 3 points, okay. No, it is the same, and divided by what? Not 1. No, come on. What is the denominator of equation 2? Delta x whole squared, right? Right. So, you are probably forgetting what is meant by this. This means electric field at t is equal to n delta t and x is equal to x naught plus I delta x. Now, hopefully it is clear. Each of the points in space are apart, spread apart by delta x. Each of the time instances are spread apart by delta t. That is the discretization in space and time. Fine. And this is therefore going to be equal to 1 by c squared. Okay. So, now what should I write this as? First term, I am trying to approximate the time derivative, second time derivative. So, E, what do I write? What point in space should we choose? The simplest point in space, I, very good. Time, n plus 1, that is right, because now I am taking a time derivative. So, I have to take different grid points in time, minus next term 2 E n I plus E n minus 1 I divided by, how far apart are they in time? Not 1, delta t. So, what should the denominator here be? Not delta t squared, something else, forgetting a factor of c, that is coming from the wave equation. So, this is what our wave equation, which was very nice to look at in continuous coordinates, but in the discretized version these are all the terms that will be there, right. So, I am discretizing space, I am discretizing time. Okay. So, in this figure you can think of these other two instances, if this is time over here, right. So, these are the 5 sort of stencil points that are being used. The grid size remains the same. I am evaluating my function at grid points spaced apart by delta x delta t. But now to approximate f double prime, I need 3 values of f. Earlier I needed 2 values. Okay. Is this figure clear, or should I draw it again? It's clear, right? There's x and t is the vertical dimension. So these are 5 points, 5 point stencil which is used to evaluate this function. Okay, notice the midpoint is common, E and I is common. Alright, so now we want to see what kind of a wave flows on such a grid, which has a finite delta x and a finite delta t. In the limit, of course, it is correct, right? In the limit, it will give me the differential equation, but when I choose some finite delta x and finite delta t, what happens? Okay. And I know what the solution should be, right? Solution should be a wave. Okay. So, what we will do is, we will assume, this is a common technique in numerical analysis, you assume a kind of a trial form of the solution that you expect it to be and substitute it in. Instead of trying to derive it from the equations, we will assume a trial form and push it into the equation and see whether it works. Okay. And this trial form should be general enough to give wave solution and non-wave solution also. Then we can see what is the solution giving me. Okay. So, the trial solution, we are going to take something like this. So, we will keep the wave in space, okay, and we will question whether we are getting a wave in time. That is the strategy that we will follow. So, I am going to write E n I in this following form. Let us take a moment to absorb this. What am I saying over here? The trial solution is of this form where there is a wave in space, alright, and there is some alpha term in time. Okay. This x is simply the discretized version, so I delta x. Okay. I is your integer, not your complex iota. Okay. The correct solution has what? For the correct solution, what is alpha? Not 1. Yeah, e power j omega t, right. So, this alpha is little bit more general than e to the j omega t. E to the j omega t is a phasor, but supposing alpha turns out to be a pure exponential, like a purely decaying exponential or purely increasing exponential, that can capture, it can be, for example, alpha may turn out to be e to the beta t, where beta is some complex number. Then what will happen? Our solution is no longer a wave, it is attenuating or increasing, something which is not physically expected in this situation. So, we have chosen this solution because it captures a variety of solutions. Alpha is, yeah, you are right, alpha is actually delta t, yeah. So, n, it is alpha to the power n, so n delta t becomes my t. What would we do now? So, what does the question become? Question will become, if so, we will take this form over here 4. So, the question is as follows, put 4 into which equation? Into 3, and then ask do we get a wave? Then life is good, everything is consistent, my system of, my way of discretizing is fine. So, I will give you a hint. When we try to answer this question, we will get some condition on delta x and delta t, which will, and under those conditions the solution is a wave. That is what will happen. Okay. Okay, so let's try to substitute this in. So, let us take the left hand side of equation 1. What will I get? So, E n I plus 1. Okay, so we will just write this over here. So, alpha to the n e to the minus j k delta x I, that is my E n I. Okay. So, E n plus 1, sorry, E n I plus 1. So, what will happen? So, notice that all the terms on the left hand side and the right hand side have one factor in common, which is E n I. They are all exponential, so they are all multiplied with each other. So, this E n I term will be basically common. So, that is going to be e to the minus j k delta x I. This is going to come out to be common. First term E n I plus 1. So, what will this first term be? So, alpha is going to remain constant everywhere, alpha will be here because you can take alpha to the power what, n, right, and next term is going to be e to the minus j k what. We are substituting 4 into 3. Okay. So, I am asking you what is the first term of 3, left hand side of 3, first term, having substituted this? Delta x, very good. Next term is going to be a minus 2, that is n plus 1, right. So, look at the term I have taken outside the bracket, multiply that by the term inside, I get I plus 1 times delta x. Second term is 2 alpha n, anything else? That is all. Final term is alpha n e to the power j k delta x, right, is equal to, so the delta x square I will take on the other side. Again over here I can take out e to the minus j k delta x I common from here. So, the first term will become alpha n plus 1, anything else? No, minus twice alpha n plus alpha n minus 1, anything else? No, into these remaining constants, right, which is delta x by c delta t whole square. Okay. So, there is a lot of terms that we can see are getting cancelled from here. So, what terms get cancelled? The exponential gets cancelled. Does any alpha get cancelled? What is the most convenient power of alpha to cancel off from both the left and right hand side? Alpha to the power n minus 1, right, the last term on the right hand side. So, this will further simplify, we can cancel it off. So, the first term is going to become, what will it become? So, alpha to the power n minus 1. So, this alpha will come outside, let us say, I am cancelling alpha to the n minus 1. So, e to the minus j k delta x plus e to the j k delta x, what is that? Not 1, come on, e to the j theta plus e to the minus j theta, 2 cos, right. So, that is going to be 2 cosine k delta x minus this 2, e to the minus j theta plus e to the j theta is 2 cos theta, that is what I got. And the right hand side I cancelled alpha to the n minus 1. So, the first term will be alpha squared minus 2 alpha plus 1 delta x by c delta t whole square. So, in terms of your, I mean, what kind of equation is this in alpha? Alpha is the guy that I am trying to solve for. So, is it a quadratic equation? It is a quadratic equation, right? So, I can write this, further simplify this in the quadratic form. So, I am going to get a alpha squared, okay. This delta x by c delta t square I will push to the left hand side. Cos, so 2 cos kx minus 1, sorry 2 cos k delta x minus 2, can we simplify that in terms of half angles? I will write it as sin squared k delta x by 2, right, and there will be a minus 1 over there, yeah. So, I will write down the final form that you get. Okay. So, I moved this delta x by c delta t square to the other side, that 2 cos theta minus 2 became minus sin squared theta by 2, that is your term over here, right. Very simple algebra, right, there is nothing very complicated about it, okay. And so, this whole term over here, I am just going to call it some capital A, so simplicity. So, we are almost there. We want to now look at what is the kind of solution that I get from here. So, in other words, what alpha do I get?